All right, so basically, last lesson we were speaking about if you drop a spherical ball into a liquid, it will eventually accelerate and reach terminal velocity, and then the forces are balanced in this scenario. And we rearranged the equation to work out the terminal velocity, and also we've rearranged to work out the viscosity. And this is the equation for the viscosity. And in order to calculate the viscosity, we said that we need to measure the radius, measure the density of the ball using mass over volume, where the volume is 4/3 pi r cubed. The mass from electronic balance, the density of the fluid using a measuring cylinder, terminal velocity using the distance over time. And we spoke about different methods. We spoke about what we must consider, for example, when measuring the radius, use a micrometer instead of a ruler because it has a higher resolution. We spoke about all of this, to be fair. And basically, once we've done all of this, let's say you did this practical in class and you measured everything you needed to measure, and then you plugged it all into the equation. Viscosity is 2r squared g pb minus pf over 9v, and you got final value for the viscosity. You did all of that. The question is, how confident are you with your final answer for viscosity? And what are some reasons your answer may not completely match the true value? So what do you both reckon? What are some reasons your answer, your calculated answer, may not match the actual true value for the viscosity of the liquid?
So for like factors, maybe like the concentration of the fluid or something like that.
What do you mean by the concentration?
Like so the amount of, okay, just never mind.
Sir, maybe you weighed the ball wrong, for example.
Yes, but in physics, we always assume that, how do I put it? We always assume that you did the experiment correctly. Like
Okay.
You don't assume someone weighed it wrong. But let's say you did everything correctly, you measured everything correctly, you measured at eye level, you got rid of the zero error, the systematic error, you did all of that properly, and you got your answer. Would you expect your answer to be completely identical to the real value, or may it vary slightly?
Sir, it would vary slightly. Sorry, I think I know maybe why. Sir, if you want a really true value, would need to repeat the experiment a lot of times.
Okay, but why would
Is
it
that
vary
why?
slightly? Why do you reckon it will vary slightly?
I don't know.
Okay. Let's say you measured the height of yourself to be 183 centimeters. Do you reckon your height is exactly 183.000?
No.
Why not? That's what you measured.
Sir, sir, is it because the ruler or whatever you used to measure doesn't get that accurate?
Excellent. It's to do with your measuring instruments, your ruler, your stopwatch. For example, the stopwatch, there's human reaction error, right? So that may have made your answer slightly different because that would have changed the velocity, which have changed the viscosity. Or maybe there was some error in using the ruler. Maybe the ruler isn't that precise, meaning the best your ruler could do is 183. So the real answer could be 183.45798, where you had to round because that's the best your ruler could do. So it's to do with your instruments used. Good, excellent. So these are all reasons that are going to perhaps impact your answer. So,
hi, sir, can you hear me?
Yes, I can. Yes.
Okay.
So for every measurement in physics, there is something called an uncertainty. And this is the maximum possible difference between the measured value and the true value due to the limitations of the resolution of the instrument. We'll talk about what that means soon. The resolution of an instrument is the smallest possible measuring interval. So for example, if I measured the length of, what is that? I measured the length using a ruler. So here's my ruler of, let's say, a pencil. And I said, oh, the length of the pencil is 11.3. The smallest possible interval is 0.1 centimeters. That is the smallest possible measurement your ruler could do. Smallest possible interval. Your ruler cannot say it's 11.378 because it's not within its ability. So this is called the resolution, the smallest possible measurement a ruler could take. If you get a voltage reading of 35.7 volts on your voltmeter, the resolution of this voltmeter is 0.1 volts, because clearly it's going up in 0.1 volts, 3.7, 3.6, 3.5. This is the resolution, again, the smallest possible interval. So this is what resolution is. Copy down what the definition of resolution, and then copy down the second one, which is the definition of uncertainty. So uncertainty is the maximum possible difference between the measured value and the true value due to the limitations of the resolution of the instrument. Don't worry, this will all make sense shortly.
Sir,
Mhm.
I joined a few minutes late, so did I miss anything, or is it just uncertainty and resolution?
No, you didn't miss something. We were just saying, in the practical we covered last lesson, we spoke about the viscosity. Let's say you did everything correctly and you measured the velocity, the radius, the density, and you plugged it into that equation. You would have got your final answer for viscosity. However, how certain are we that this answer we measured, we obtained, is the exact same as the true value? And now we're talking about the things that might impact it. Finished?
Just a second.
Yes, sir.
Yeah, finished.
Okay. So, for example, the ruler, as we spoke about, has a resolution of 1 millimeter or 0.1 centimeters. They're the same thing. So it goes up every millimeter, or it goes up every 0.1 centimeters. That is the best your ruler could give you. Your ruler cannot give you a more precise measurement. Okay, let's go back to the slides. Let's say you measure the length of a pen using a ruler. It would be ridiculous to say the measured length is 15.6543. You can't say that's the length because you use the ruler. After all, where did you get all these significant figures from? Certainly not the ruler, because the resolution of your ruler is just 1 millimeter. So the best you could have got is 15.6 or 15.7, correct? That's the best your ruler could have given you. So if you quote any other values, like where did you get the values from? You made them up. Okay, so let's say the ruler measured 15.6, use your ruler, and you measured 15.6. And that's the length of a pen. How certain can you be with this measurement? How certain are you it's exactly 15.6? Is it 15.660000000? Do you reckon that's the case?
No.
No.
No, okay. Could it have been 15.634? Is that possible?
Yeah.
Okay, that's possible. How about 14.8?
No.
Yeah, 14.8 is not possible. 15.634, yeah, that's possible within the ruler. But if you measured 14.8, then something went wrong. Either there was like a big parallax error, or you just didn't know how to measure it properly, or there's a zero error, blah, blah, blah. So the question is, what is the range of possible values for the true value of the pen, assuming the procedure was carried out correctly? So the human measured it correctly, he measured at eye level, blah, blah, blah. And he measured 15.6. What's the range of possible values?
Sir, I think I have an idea.
Go on.
Sir, would it be from 15.5 to 15.64? I mean, 15.55 to 15.64, because it like gets rounded to 3 SF.
Beautiful, fantastic. So just recap one last time, everything we've done so far. So we said that every measurement in physics, there's an uncertainty. And this is the biggest difference between the measured value and the true value. And we said every instrument has a resolution, and the resolution is the smallest possible measurement you're able to get from the instrument. For example, this ruler is 1 millimeter. Then we said if we were to measure the length of the ruler, the best we could get is 15.6. You can't say you got 15.65 because your ruler, that's beyond the resolution of your ruler. So how certain are you if you measured 15.6? What's the range of possible values? And fantastic, as was said, we say that a meter ruler can easily be read correctly to 0.5 millimeter. So when you're looking at the length, and let's say, here's the tip, as your ruler. Actually, let's do it a bit like this. 2, 4, 5. And the tip of your pencil was around here, right? You could easily round this to the next point and say, oh, it's 0.2 centimeters or 2 millimeters. You could easily do that. So you could easily round to the nearest 0.5, because if your pencil was here in this position, no one's going to round it to this one. It's easy to tell. It's easy to tell that, oh, this is probably closer to 0.1 than it is 0.2. You can't say it's 0.1345 and just guess. You can't do that either. It's either 0.1 or 0.2, and clearly it's closer to 0.1 then we could put it at 0.1. But the problem is, if it's right in the middle, that's when it becomes a little bit problematic. Because now you can't tell if it's 0.1 or 0.2, but it doesn't matter. You could either put it at 0.1 or you could put it at 0.2. The actual value is 0.15. 0.1 is 0.05 away from this, and 0.2 is also 0.05 away from this. So the maximum possible difference is 0.05, right? So what's going to be the range? Well, we said we've measured 15.6. centimeters. The range is going to be from 15.55 to 15.65. It could be 15.55, it could be 16.55, or it could be any value that's in between them. For example, 15.59782 2, 1. Any value in between these two is possible. Any value outside these two means you didn't measure it correctly. Sorry, you didn't measure it correctly. Does that make sense? Raise your hands if so far you're following. Goes on. Any part you didn't understand? Okay. So the value obtained is therefore 15.6 centimeters plus minus 0.5 millimeters or plus minus 0.05 centimeters. This plus minus 0.5 millimeters, this is your uncertainty. This is how unsure you are, the maximum possible difference. It could be 15.65. It could be 15.55. So this is what we call the uncertainty. It's always better to keep it consistent. So if your measured value is in centimeters, like 15.6 centimeters, then you should also have your uncertainty in centimeters. So the blue one's the better way to put your answer. So in GCSE, it was enough to say, oh, I measured the length to be 15.6. In A level, that's no longer acceptable. You have to say the measured length is 15.6 plus minus 0.05. You're telling the examiner, you're telling whoever's reading your paper that the value could be 0.05 higher or 0.05 lower. And by extension, you're telling them what equipment you use. So this is what we call uncertainty. So the maximum possible difference. And in this case is 0.05 centimeters. Generally, the uncertainty is just half the resolution. So for the case of the ruler, the resolution was 1 millimeter. So the uncertainty was 1 divided by 2, which is 0.5 centimeters. 0.5 millimeters, or 0.1 centimeters, which is the resolution, divided by 2, which is 0.05. If you were to measure the voltage across a resistor as 15.4, the uncertainty will be 0.05, as the smallest reading is 0.1 volts, and half of the resolution, half of 0.1 is 0.05. Okay, the first question for you guys to have a go at, write down the following measurement, include the units and uncertainty.
Sir, do I answer it?
Yes, we're done.
Sir, so it's 0.8 volts with a plus or minus 0.1.
Excellent. So 0.8 volts, that's the measurement. What's the uncertainty? Well, the resolution is 0.2. That's the smallest possible reading. So the uncertainty is half the resolution. So 0.2 divided by 2 is 0.1. Therefore, your answer is 0.8 volts plus minus 0.1 volts. Okay, excellent, beautiful. How about this?
So is the value 0.65 amps?
The value looks like is 0.24, 0.62.
You can't say 5.
Good, excellent. So that's correct. You can't say 5 because it goes up in 0.02s. So where did you get the 5 from? You guessed. That's like someone saying, oh, the length is 15.653825. He added random stuff that wasn't available. And so did you. You could only ever go up in 0.02s here. So 0.62, 0.64, or 0.66. It looks like it's in the middle. So you're going to have to pick. Pick either 0.64 or pick 0.66, whatever you think is closer.
Sir, in an exam, would they give us like this kind of thing where it's in the middle? and then just allow both answers, or would they make it clear which side it's on?
Generally, you round up. If something's in the middle, that's a good question. I don't know, because I think just to be safe, round up.
Okay.
And yeah, because if you round up, you 100% will get it right. If you round down, you may get it right, you may get it wrong. So if something's in the middle, you always round up.
Sure, I think I have the answer.
What did you get?
0.66 amps, and then plus or minus 0.01 for the uncertainty.
Good. So the value is 0.66, so you round it up. The resolution 0.02, therefore the uncertainty is 0.01 because you have to divide by 2. So your final answer is 0.66 plus minus 0.01 amps. Fantastic, beautiful. Very good. So yeah, slight difference than GCSE because we have to consider the uncertainties. So let's talk about uncertainties and averages. So this is just one. Let's say you took one reading and you got this. You just do half the resolution. The uncertainty is just half the resolution when you take one measurement. However, what if you take multiple measurements? For example, a student measures the diameter of a metal canister, so like a metal can, and he used a ruler, and the ruler is graduated in millimeters. Graduated meaning the resolution is 1 millimeter, right? It goes up in millimeters. So we know what the resolution is. And he recorded these values. What is the uncertainty of the diameter, of the mean diameter?
Sir, do you add up all the uncertainties together? So if it was since like this one would be 0.05 centimeters. Oh, wait, this one's millimeters. So 0. Wait, sir, no, wait, I'm confused. Yeah, 0.5 millimeters. So would it be 2 millimeters for the uncertainty added up together?
That's a very good guess, to be fair. Not quite. Because even if you did that, are you saying it's 64 plus minus 0.2?
No, sir. Plus or minus. I mean, plus or minus 2.
64 plus minus 2. The problem with that is, what about reading free? Reading free is not plus minus 2 away. Reading free is 3 away. But reading free did exist. But you were saying from your uncertainty, it's impossible for it to exist. So what you may notice now is, hang on, we can no longer just do the resolution, half the resolution of the instrument, because there's more than one value. So you're going to have to do something called the half range. And what the half range is, just half of the range of the values. You guys know what the range is? The range is the difference between the largest value and the smallest value. In this case, the largest value is 66, the smallest value is 61. So half of that will be, well, the difference is 5, so half of 5 will be 2.5. So your final answer is 64 plus minus 2.5 millimeters. So just to recap, usually when you're doing the uncertainty, like in this question and this question, you just do half of the resolution. But if there's averages, so you took more than one measurement and you worked out the average, the uncertainty in the average is equal to half of the range. Half of the highest value minus the lowest value. Here, 66 minus 61 equals 5. That's the range. Divided by 2 is 2.5. So actually your mean is 64 plus minus 2.5 millimeters. Raise your hands if you're happy to move on. Faizan, Isa, are we stuck?
No, so I get it.
Okay, good. So again, it's just showing you that the range is 61 minus 66, or 66 minus 61 divided by 2 is 2.5. So your final answer is 64 plus minus 2.5. Good. Now have a go at this yourself. Work out the mean length of the gerbil. So here's a table showing how someone measured the length of a gerbil and he repeated 5 times. What is the mean length of the gerbil? Include the uncertainty.
Sir, I have an answer.
What did you get?
Sir, so the mean length would be 32.4 centimeters, and for the uncertainty, it would be plus or minus 1 centimeter.
Okay. We'll let everyone else have a go. While everyone else is have a go, I'm just going to tell Joanne what we did so far. Just screenshot this because I'm about to go to the other slides. So what we said, Joanne, is for every measurement, there's something called an uncertainty. And for every instrument, there's something called the resolution. The resolution is the smallest possible interval in your device. So for example, when you're measuring using a ruler, the resolution is 1 millimeter because the ruler goes up in 1 millimeter. So, or 0.1 centimeters. So 0.1, 0.2, 0.3, that's the resolution. And we said that if you measure the length of a pen using a ruler and you get 15.6 centimeters, you could be off by a little bit, depending on the resolution of the ruler. And the range of possible values is 15.55 and 15.65, right? So the actual length of your pen could have been 15.62345. But obviously when you use the ruler, you had to round. You had to like guess like where's the closest line it reaches. And this is called the uncertainty. So the uncertainty is the maximum difference between the true value and the measured value. And it's equal to half the resolution of the instrument. So for a ruler, the uncertainty is 0.05. Let's say you measure the voltage of a voltmeter as 15.4. The uncertainty is the resolution. Well, what's the resolution? Is 0.1. That's the smallest possible measurement because it's going up in 0.1. So 15.4, 15.5, and you half it. So uncertainty is half the resolution. It has an example. So the value is 0.8 volts, and the uncertainty is the resolution, which is 0.2 because it's going up in 0.2s. Divided by 2, which is 0.1. So the answer will be 0.8 volts plus minus 0.1. And then we said, however, when you're doing averages, the uncertainty is no longer the half the resolution. What you have to do is something called the half range. And all the half range is you work out the range of your values. In this case, the range is between 66 and 61, which is 5, and you divide it by 2. Which is 2.55. So that is your uncertainty. That's why it's called half range, because you're literally halving the range. So when you have more than one measurement and you do repeat readings, so every time there's repeat readings, you may have to use the half range. Now the question is, work out the half range of the following. So first of all, work out the mean. Sorry, it says work out the mean and include the uncertainty. Who else did this question and got an answer? Okay, so I know how you all started. You started by working out the mean. So you did 32.6 plus 33.1 plus 33.8 sorry, plus 31.1 plus 32.8, because we're working out the mean, plus 32.4 divided by 5, because there's 5 measurements. Let me do that quickly on my calculator. Divided by 5. Is that what you guys got? 32.4?
Yes, sir.
Okay, so the mean is 32.4. I'm not going to write 32.44 because I can't use a higher number of significant figures than what they've given me. Doesn't make any sense. So that is the mean, 32.4. Now the question is, I need to work out the uncertainty. Well, because there's repeat values, I need to use the half range. So what is the range? What's the smallest, the largest value minus the smallest? Well, the largest is 31.1. Yep, the smallest, sorry, the largest is 33.1, the smallest is 31.1. So the range is 2 centimeters. Half of the range is 1 centimeter. So you get 32.4 plus minus 1 centimeter. That is your final answer. So you worked out the mean, you worked out the range, you divided it by 2 to get the half range, and the half range is your uncertainty. Meaning I could be off by 1 or I could be off by -1. There's a problem with this though, and we're going to talk about it now. And the problem was this, we said the uncertainty is ±1. However, notice that 32.4 minus 1, which is supposed to be the lowest value, is 31.4. However, we got a value of 31.1. So one of the values didn't even fit the uncertainty. This is a problem. And in this sort of scenario, you can't really use the half range. You're going to have to use another method.
Sir,
Yes.
so I didn't want to interrupt, but I was just really confused about the 2 centimeters divided by the 1. I didn't like, where'd you get the 2 centimeters from?
So we're working out the uncertainty U, and the uncertainty is half of the range. So the range divided by 2. What is the range? Is the
It's
largest
the largest value, yeah.
divided by smallest, which is 2.
So you always, to find the uncertainty, divide the largest, minus find the range and then divide it by 1.
Divided by 2.
Divided by 2, and then it's just plus minus that value.
Good,
Okay.
excellent. Yeah. So you did half the range divided by 2. We got 1 centimeter. That is the uncertainty. So wherever you get plus minus 1 centimeter. But the problem was that one of the values didn't lie within this. It didn't fit. And we can't just say it's an anomalous result. You can't do that in physics A level anymore. So we're going to have to find a different method to work out the uncertainty. And it's the method called the furthest value from the average. So what you do is, first of all, you work out the average, which is 64. And then you decide what is the furthest value from the average. And in this case, the furthest value from the average is 61. And what's the difference between the mean and the furthest value? The difference is 3. 64 minus 1 is 3. And that is your uncertainty. So this is the third method to work out the uncertainty. So the first method is when you have one measurement, you do half of the resolution of the instrument. The second method is when you have multiple measurements, you do half the range. The third method is you have multiple measurements again, but the half range doesn't work because one of the values doesn't fit. Then you have to use something called the furthest value from the average.
Sir?
Yes.
Sir, for this this way of doing it, it doesn't matter if the reading is higher or lower than the average, right?
Yeah, it doesn't at all.
Okay.
Good. So it would just be 64 minus 61. That's 3. Your uncertainty is 3, meaning your mean is 64 plus minus 3. I'm going to give you a question for you guys to do on your own now. So go back to this example, work out the mean and include the uncertainty. We already worked out the mean is 32.4. What is the uncertainty? But I want you to use the furthest value from the average because we just discussed that the half range isn't the best thing we could do here.
Sir, I have an answer.
Yes?
Would it be 32 plus 32.4 and then plus or minus 1.3 centimeters?
1.3. Good. That is correct. So you have to work out what's the furthest value from the average. The average is 32.4. What value is furthest away from that? Well, it's 31.1. So you do 32.4 minus 31.1. You get 1.3 centimeters. That is your uncertainty. So actually, your mean length is 32.4 plus minus 1.3. Why is this better than the half range? Well, now all of the values lie within this. So 31.1 now fits. Before we had 32.4 plus minus 1. So 31.1 didn't fit in this range. But now all of the values fit within the range. Now, most exam questions, they'll tell you what method to use. So they'll be like using the half range or using the furthest value. And some questions, they are very lenient as well. So let's say you used the half range when you were supposed to use the furthest value, they still accept your answer. But very rarely, sometimes they expect you to use the right method by realizing the half range doesn't work because the value is too far away. So I need to use the furthest value from the mean instead. Good. So uncertainty averages, which method do you use? So let's say you measured something and you got the average, what method to use? So for single readings, i.e. there's no average, the uncertainty is always just half the resolution. We did that at the start. So for the ruler, it's half of 1 millimeter. But for averages, we do the half range or the furthest value. I literally just said this. Anyway. Here are your following cases that I want you to write down and know. So case one, there's a single reading, like the length of a blah, blah, blah. And in this case, you use half the resolution of the instrument. The second case, there's repeat readings, but they're all the same value. And in this case, you also use half the resolution. We'll talk about case two later. Just copy it down for now. Case three, there's repeat readings and the mean lies within the middle of the upper and lower values. Then you use the half range. And then finally, there's repeat readings and the mean is significantly closer to 1. So some of the values don't fit. And that way you use the furthest value from the mean. This is all from your syllabus, by the way. I haven't added anything extra. I tried to make it as simple as possible. We finished?
Yeah.
Okay, I'll take that as everyone's finished. Okay, let's carry on. So case 2, we said we'll discuss. Well, let's say I measured the length of a pencil and I got 15.6. Then I measured it again, I got 15.6. And I measured it a third time, I got 15.6. If I use the half range, I would get 0 because the range is 0. Can I say the uncertainty is 0?
No.
I.e., can I say it's exactly 15.6? Of course not. So I'm going to have to use some sort of uncertainty. And in that case, I'll just use half the resolution of the instrument. Does that make sense?
Yeah.
How about Isa, Joanne, Saleh?
Doctor,
Sir,
can you
yeah,
say
I
it
said
again?
yeah.
I explained it one last time. So let's say I was measuring the length of a pencil and I got measurement. Repeat 1, repeat 2, repeat 3. And I measured the first time to be 15.6, second time 15.6, third time also 15.6. I can't do the half range because the range over 2 is 0 over 2, which is 0. So I can't say the uncertainty is 0 because if I'm saying the uncertainty is 0, I'm saying it's exactly 15.60000. That's not the case. We know that's not the case when you measure the length of the ruler. I can't do the furthest from the average because the average is 15.6 and the value furthest from the average is 0. So I can't use the furthest from the average and say it's 0 millimeters again. So what can I do? Well, I'm going to use the smallest possible uncertainty, which is just going to be half the resolution of the ruler. So 1 millimeter divided by 2, or half the resolution of the instrument. So in the case where all your repeat readings have the same value, you can't use the half range and you can't use the furthest value because it'll give you 0. So you just have to use half the resolution of the instrument, as you do with a single reading. So that's what case 1 and 2 is. Okay, now we're going to talk about percentage uncertainties. Uncertainties can be expressed as percentages. For example, instead of saying that the length of the pen is 15.6 plus minus 0.05, I could say that the length of the pen is 15.6 plus minus 3.2%. Because sometimes percentages are easier to understand as humans than numbers. It's a lot easier to visualize what 3% of 15.6 is than what 0.05 centimeters is in some context. Because everyone knows what 3% is. It's just a fraction, 3 over 100. 3% of the ruler, it could be 3% larger or 3% shorter. So that's why it's sometimes useful to talk about percentage uncertainties. So can you deduce how I converted the uncertainty into a percentage? What did I do? How did I go from 15.6?
Sir, when I did 0.05 divided by 15.6 times 100, it gave me 0.32%, not 3.2.
Let me try that. Give me 2 seconds. Someone's knocking my door. Hello? I'm back, sorry. Okay, so can you just converted it? So what you do is you do the uncertainty over the measurement. So 0.05 over 50.6 times by 100, and you should get 0.32%. Why did I write 3.2%? I don't know. That's a mistake. Is that what you were saying, Saleh?
Yes, sir.
Yeah, so this should be, if I could correct it, 0.32%. So good. So what is the equation to work out the percentage uncertainty? It's the following. It's always the same. It's the uncertainty of the measurement divided by that measurement times by 100. So in the previous case, the uncertainty of the measurement is 0.05. The measurement is 15.6. That's what you measured. And then you times it by 100. So this is how you go from the uncertainty to a percentage uncertainty. Okay, so let's move on. Have a go at this question. So Beatrice measures the voltage across her iPhone charger to be 2.4 plus minus 0.05 volts. 0.05 is the uncertainty, 2.4 is the measurement. Express the above as a percentage uncertainty. And the second question is, Genevieve measures his yearly energy consumption to be 3412.8 kilowatt hours. Write down his measurement with a percentage uncertainty included. So have a go at both questions. You do know everything you need to know to answer these.
Sir, I'm confused how to do the second one.
I'll give you a clue. Remember that uncertainty is half the resolution, and the resolution is the smallest possible value.
Yes, sir, I know that, but like, do I just assume that the resolution is 0.1? Because it could also technically be 0.2, because like 0.2, 0.4, 0.6, 0.8. So
That's
should I
true.
just
That's
assume it's
actually,
0.1?
yeah, you'd assume it's 0.1 always.
Okay.
Okay, so let's have Isa explain to us how you do question 1 and what did you get?
So for question 1, I divided 0.05 by 2.4 and then 2.4 and then multiplied by 100, and I got 2.08% as a percentage uncertainty.
Good, excellent. Question 2, did you do that as well?
Yeah, I did it. So you said we assume that resolution is 0.1, right?
Yes, it will be 0.1. So 3 for 1, 2.8.
Plus minus 0.05.
Plus minus 0.05 is the uncertainty, but what's the percentage uncertainty?
0.05 divided by 3412.8 multiplied by 100, and I got 0.0015.
Okay, excellent. So yeah, the first one is just literally 0.05 over 2.4, and the second one is 0.05 over 3412.8. Obviously,
Sir,
multiply both by 100. Yes.
for the first one, instead of writing 2.08, I wrote 2.1. I like rounded to 2 SF. Would I get it wrong?
No. The first one, you would have to actually do 2.1%. You have to match the significant figures given in the measurement. This is a rule for your percentage uncertainty. Or you have to match the decimal places. So if the measurement is given in one decimal place, the percentage uncertainty has to be given in one decimal place. Does that make sense? Let's just write
Yes,
that down
sir,
in
thank you.
words. Make sure the percentage uncertainty has the same decimal place as the measured value. Okay. Let's continue. Now, what if there's multiple measurements? Well, let's have a look at the first instance. What is the diameter of this ball? Include the uncertainty. So let me just transfer it here. I know some of you are using your laptops and it's hard to tell. So I'll just draw like the line for you, I guess.
Sir, I have an answer.
What did you get?
The diameter would be 2 and then plus or minus 0.5.
Okay, we'll check if that's right. We'll give our nurse 5 more
No, wait,
seconds.
sir, I think I got it wrong, sir. Wait, I'm gonna redo it.
Okay, so first of all, let's ask Joanne. Joanne, what is the diameter of the ball? Joanne, you here? No. Muhammad, what's the diameter of the ball?
It's 3.
3. So this is 68.1, 2, 3, 4. So 68.4. 1, 2, 3, 4, 5. So this is 68.5. And this is 71.5. Good. So the diameter is 3. Obviously, if it's a ruler, that will be 3 millimeters. Sorry, 3 centimeters. So the diameter of the ball is 3 centimeters, and it wants the uncertainty. What's the uncertainty, Muhammad?
Plus minus 0.5 centimeters.
Oh, plus minus 0.5 centimeters. So you're saying it could be 3.5 centimeters and it could be 2.5 centimeters. Does that sound right?
Oh no, no.
Sorry, I got a different answer.
What did you get, Saleh?
Plus or minus 0.05.
Good. So plus or minus 0.05 centimeters. That sounds more right, because that means it could be 3.05 or 2.95. However, this is actually incorrect. And who wants to tell me why? Why is it not 0.05 in this particular instance? Okay, to measure the diameter, first you had to take a measurement here. And when you measured 68.5, there was an uncertainty of 0.05. Then you had to take another measurement here. And when you took the measurement of 71.5, there was another uncertainty of 0.05. So each measurement had an uncertainty. Does that make sense?
Yes, sir.
So the overall uncertainty is going to be a maximum of this plus that. So the final answer should technically be 3 centimeters plus minus 0.1 centimeters. Because you could be 0.05 off for the first measurement, and then you could be 0.05 off for the second measurement. So it's potentially possible to now be 0.1 centimeters off. Good, let's continue. So most calculations in physics involve
Wait,
taking
sir?
what? Yes.
So can you go back?
Mhm.
So you add the uncertainties. So don't you then divide by 2 or?
That's when you're doing the resolution. To get the uncertainty, you do the resolution divided by 2. But we already have the uncertainty. The uncertainty,
Okay. Yeah, I get it. Okay.
yeah, uncertainty is 0.05. But there's an uncertainty for the first one and an uncertainty for the second one. You have to take 2 measurements. So yeah, and that's why the following slide is saying in physics, sometimes it involves you taking multiple measurements. Here, you have to take 2 measurements. Sometimes you have to take more than 2 measurements. Let's say you're measuring. Let's say you're measuring the volume of this cuboid. How much measurements do you need to take?
3.
Good guess, but that's not true. So you have to measure the base. You have to measure the height. You have to measure the width. You might think that's 3, but actually to measure the base,
Yeah,
you
they're
have
the
to take.
same.
No, that's not it. To measure the base, you have to take 2 measurements. The first measurement to start the ruler, you could be up to 0.05 off, and the second measurement to get the end. Does that make sense? So every single length required 2 measurements. So technically it's 2 measurements, then 4, then 6. So there's 6 measurements here. So what's the total uncertainty? It will be 0.05 multiplied by 6, because you had to take 6 measurements overall to get the volume of this cube. Okay, let's continue. So yeah, in physics, you have to take multiple measurements. Each measurement has its own uncertainty. It is therefore necessary to combine the uncertainties of the measurements to acquire an overall uncertainty of the calculation. Like in this question, we have to combine all the little uncertainties, which was 6 times 0.05. And only then we get the overall uncertainty. Now, there's different cases in physics. Sometimes you have to add variables. Sometimes you have to subtract. This case, you have to subtract. Sometimes you have to multiply. Sometimes you have to divide. And we're going to cover all the different cases. So case one, if a calculation involves the addition or subtraction, then it is enough to just add the uncertainties. So if it involves addition or subtraction, here it involved subtraction, here it involved addition. In these scenarios, all you have to do is just add the uncertainties. So let's do an example. Let's say you measured the EMF of your circuit, so the total voltage of the circuit, as the voltage across the first resistor, plus the voltage across the second resistor, plus the voltage across the third resistor. And you measured the first voltage to be 2.4. You measured the second voltage to be 5.1, and you measured the third voltage to be 2.9. What would the uncertainty be of the total voltage?
Sir, would it be 0.05 times 3?
Excellent. Isa, why do you reckon he said that? Can you explain to us? Why is it 0.05 times by 3?
Because you have three uncertainties. You have three
Measurements.
measurements. Yeah, measurements.
Good. So this one has an uncertainty of 0.05. So yeah, this has an uncertainty of 0.05 because remember the uncertainty is the resolution. The resolution is 0.1. That's the smallest possible reading divided by 2, which is 0.05. And this one has an uncertainty of 0.05. So you have to add them up. That's the first case. So remember the first case, when you're doing addition or subtraction, in this case, V1 plus V2 plus V3, then you just add up the uncertainties. Therefore, the total voltage is 10.4, which is 2.4 plus 5.1 plus 2.9 plus minus 0.15 volts. And if you wanted to convert it into a percentage uncertainty, then you do 0.15 divided by 10.4 times by 100. So you could have expressed it as 10.4 plus minus 1.4%. So yeah, you could give it as uncertainty or you could give it as a percentage uncertainty. The examiner will tell you what he wants it.
Sir,
Yes.
so can you explain again how you calculated the uncertainty?
Okay. So the uncertainty of a single measurement is half the resolution. So when you measure 2.4, the uncertainty is half the resolution. Well, what is the resolution? If you have a voltmeter and it reads 2.4, what do you think the smallest possible interval is? 0.1, right? Because it's going to go up in 2.4, then 2.5, then 2.6. It's going to go up in 0.1s. So what's the resolution of something that gives you the reading 2.4? The resolution is 0.1 volts. Does that make sense so far?
Yeah.
And the uncertainty is the resolution divided by 2. So the uncertainty is 0.1 divided by 2, which is 0.05. This is your uncertainty. So when you measured the first one, you had an uncertainty of 0.05. You could be up to 0.05 of the real answer. The second one, again, you could be up to 0.05 up from the answer because it's the same voltmeter used. And the third one also 0.05. So now what is the uncertainty? Not of V1. I know what the uncertainty of V1 is 0.05. Not of V2, not of V3, but of E. E is V1 plus V2 plus V3. So the total uncertainty is going to be the sum of all these uncertainties. It's going to be 0.05 plus 0.05 plus 0.05, which is 0.05 times by 3, which is 0.15 volts. That is the total uncertainty of the total voltage. Does that make sense?
Yeah, I got it. Thank you.
No problem. Okay, so case 2 is multiplication or division. So if a calculation involves multiplication or division, then we must add the uncertainties. Let me give you a basic example. Let's say you're working out the voltage across a resistor, and I know that the resistance is 30 ohms, and I know that the current flowing through the circuit is 2.1 amps. The question is, what is the voltage and what is the uncertainty? Well, the voltage is just current times resistance, so 30 times 2.1. Which gives me 63. So V is equal to IR equals 30 times 2.1 is equal to 63 volts. So that is the voltage. Now the question is, what is the uncertainty of the voltage? Well, there's an uncertainty thanks to the current, which is the precision, which is 0.1 divided by 2, which is 0.05. So the uncertainty in the current is 0.05. The uncertainty on the resistance, well, what's the resolution? Here is 1. You're going to assume is 1. Unless it said, if it said 30.0, then you're going to assume is 0.1. So it will be 1 divided by 2, resolution divided by 2, which is 0.5. So this has the uncertainty of 0.5. Now the question is, what is the uncertainty of the voltage? It might be tempted to just add these two, but that doesn't work anymore because you're not adding the values. So you have to do something different. And instead of adding the uncertainties, you have to add the percentage uncertainties instead. So I can't add 0.5 plus 0.05 because these are the uncertainties. I have to add the percentage uncertainties. Well, let's do that. So first of all, what's the percentage uncertainty of the current? Well, the percentage uncertainty is the uncertainty, which is 0.05, divided by the measurement. Well, they measured the current to be 2.1 times by 100. So let's do that. 0.05 divided by 2.1 times by 100, which is around 2.3%. That's my uncertainty on the current. Sorry, the percentage uncertainty in the current. And my percentage uncertainty on the resistor is, well, the uncertainty is 0.5. The value is 30. So sorry. You get around 1.6%. So that's the percentage uncertainty of my current. That's the percentage uncertainty of my resistance. The question is, what is the percentage uncertainty of my voltage? Well, it's going to be 2.3 plus 1.6, which is 3.9%. So when a calculation involves multiplication or division, what you do is you add the percentage uncertainties. If a calculation involves addition, like let's say A is equal to B plus C, then what you do is you add just the uncertainties. But if it's B times C, you don't add the uncertainties, you add the percentage uncertainties. And that's the rules that you have to follow in your spec. I guess you don't need to know why that's the case. I don't really have the time to explain why that's the case here. So let's have a go at this. Primrose set out to calculate her average speed during a 100-meter sprint. She measured the 100-meter distance using a measuring tape with resolution 1 centimeter. Her friend Miranda measured the time using a stopwatch. She measured 12.42 seconds using a stopwatch. Determine her average speed, include a calculation of the percentage uncertainty.
So what's the resolution for the time? 0.1 or 0.01?
It'll be 0.01.
01, okay.
So we go 2.42, 2.43, 2.44. So it'll be 0.01.
So I got an answer.
What did you get?
I got 8.05 meters per second plus minus 0.01%.
It's minus 0.01%. Okay. So let's solve this question step by step. So obviously determine the average speed. We'll start with that. Speed is distance over time, which is 100 over 12.42. Which is 8.05, as you said, excellent, 8.05 meters per second. Now the question is, what is the uncertainty? Well, in this case, a division is involved. So remember, we said if there's division or if there's multiplication, you don't add the uncertainties, you add the percentage uncertainties. So first of all, what is the percentage uncertainty of the distance? Well, it's equal to the uncertainty of the ruler, which is 1 millimeter or 0.1 centimeters. So 0.1 centimeters, which is 0.0001, because you want it in meters, right? The reason you want it in meters is because your measurements in meters. So it'll be, why is it 0.1, not 0.05? Because in a ruler, you have to take 2 measurements. So I have to times it by 2. So that's why I'm putting the uncertainty as 0.1. So yeah, so 0.0001 divided by 100 times by 100. I guess that's just going to be 0.0001%. Very, very small, insignificant percentage uncertainty. Because she used the meter ruler. Okay, excellent. Now let's do the percentage uncertainty of the time. So the uncertainty of the clock is 0.01 over 2, resolution over 2, which is 0.005 divided by 12.42 times by 100. Let's put that in our calculator. Is around 0.04%. So now what you do is 0.04% plus 0.0001%. This is your uncertainty of the speed. It's very small. It's 0.0401%. Very, very small uncertainty. Does that make sense? Any questions?
Sure.
Yes.
So if the resolution is, so I don't get, can you explain the how you got the percentage uncertainty for the distance?
Okay, good. So the percentage uncertainty is the uncertainty. So what's the uncertainty of a ruler? If you need to remember, you need to take 2 measurements here. You need to take a measurement at the start and at the end. because she used.
So, but she used a
wait.
measuring tape.
Oh, it's giving you the resolution. Oh, I
And
thought
it
she
gives
used
you
the. Sorry, I thought she used the meter ruler for some reason. Okay, okay. If it's giving you the resolution, then you have to do the resolution over 2. So 1/2 is 0.5
So, but don't you
centimeters.
convert it to meters?
Yeah, so
0.01?
0.05 centimeters. So is that what you got? 0.05.
That's what I got, yeah.
Okay, sorry, I got 0. Okay, I thought she used the meter ruler, but that's fine because if the question did say she used the meter ruler, then at least we know what would you have to do. Although it doesn't make sense because the meter ruler can't measure 100 meters anyway, so that was very stupid of me. But anyway, let's carry on. So, any other questions? No, okay. So anyway, I did it here. I guess the answer is here. So combining uncertainties. So if you're doing additional subtractions, for example, A equals B plus C or A equals B minus C, then you just add the uncertainties. So remember when we were doing this, we had to do B minus C. We had to do one measurement minus another measurement. We had to add the uncertainties. But in a case when you're doing multiplication or division, for example, the case we just did here, we had to add the percentage uncertainties, not the uncertainties. So what is the uncertainty of A when A is B plus C minus D plus F?
Sir, would it be the uncertainty of B plus the uncertainty of C minus the uncertainty of D plus the uncertainty of F?
Right, so
Very
it's all the uncertainties added together, right?
good. It's all add. Doesn't matter if it's C minus D, because remember here, we did something minus something. Did we minus the uncertainties? No,
No,
we
sir.
still added. Good. So it would just be all the uncertainties added together. Excellent. So A plus B plus C plus D plus F. How about this? What would the uncertainty of A be?
You add the percentage uncertainty of B and C, and then add it to D. You add D as well.
Good. Excellent. Beautiful. So percentage uncertainty of A is the percentage uncertainty of B plus the percentage uncertainty of C plus the percentage uncertainty of D. Why are we doing all of this? Well, going back to the beginning when we said we were determining the viscosity. And we said, well, how sure are we with our final answer? Let's say we completed the experiment, we measured the radius, we measured the velocity, we measured the densities, and then finally we got a value. We want to know this value we got for viscosity. We want to know what is the percentage uncertainty. Let's say we got 7.8. I want to know how much far off from the true value could it be? Could it be up to 7% off? Is it 7.8 plus minus 7%? Could it be only 2% off? This is really, really important, especially when you consider the real life. So for example, let's say you're building something. You're building a building. And then you use some sort of steel material. And a manufacturer said that this, like 1 meter of steel can withstand a force of 50 newtons. But the problem is this exactly 50 newtons? Right? It has some sort of uncertainty. It might be 50.4, it might be 49.5, it might be any other value. So he has to give you the percentage uncertainty. He might say, you know, there's 2% off. So now when you have like 2,000 meters of steel in your building, and let's say 2,000 meters times by 50, that's how much force it could stand. And let's say the wind goes through, and I know that the maximum wind, so let's do 2,000 times 2,000 times 50. So this is 100,000. So I know that 2,000 meters can withstand 100,000 newtons. And let's say I know that the maximum wind that's possible is 100,000 newtons or 99,000 newtons. Can I safely build this? No, I can't, because actually this is 100,000 newtons plus minus 2%. So maybe it could have only withstood 98,000. 98,000 is the maximum it could withstand. So in real life, you always have to deal with percentage uncertainties. So you can know what's like the upper limit and what's the lower limit. And it could be like life-changing if you make a simple incorrect calculation when making a building, when there's thousands of forces and there's tensions and there's springs and there's concrete and there's materials that could break, brittle materials, and there's so much going in and there's glass. Any sort of mistake with your percentage uncertainties when building this can cause a catastrophic failure. So that is the whole point of this uncertainties. So now that we know the rules, we could actually work out the uncertainty of the viscosity. Okay. And what it will be the percentage. So let's look at all of the values involved. This is a hard question. And let's simplify. So this is equal to 2 times radius times radius, because radius squared is radius times radius. I'm going to ignore G because we always assume G is 9.81000. That's what we assume, even though that's not the case. So we'll ignore G in the calculation. So 2 times radius times by density, which is mass over volume, minus mass over volume, divided by velocity. So I have one variable times one variable times one variable, and these variables minus each other. So first of all, let's just look at the bracket.
Sir?
Yeah.
What about the 9?
The 9 is just it's a constant. So it assumes it doesn't have uncertainty. Uncertainty 0. Assume it's 9.0000.
But then, sir, why did you include the 2 at the top?
Very good question, by accident. Good. So first you tackle this bracket, and you do percentage uncertainty of the mass plus the percentage uncertainty of the volume, right? Because it's mass over volume. Then you times it by 2 because there's a minus. Then what you do is you add that to the percentage uncertainty of the radius. So then you add it to the percentage uncertainty of the other radius, because it's radius squared. And then finally, you add to the percentage uncertainty of the velocity. Don't worry, you will not get something this hard in the exam, but you do need to understand the intricacies, because although the examiner is not going to ask you work out the uncertainty of the viscosity, because it's very unlikely, he might just tell you work out the uncertainty of the radius squared divided by the volume. So the radius squared divided by volume is equal to some constant x. Work out the percentage uncertainty of x. We're going to do the percentage uncertainty of the radius plus the percentage uncertainty of the radius, because that's what r times r, plus the percentage uncertainty of the velocity. But what is the percentage uncertainty of the velocity? Well, velocity is distance over time. You do the exact same thing we did for the Primrose question. So the percentage uncertainty of the time plus the percentage uncertainty of the distance. So yeah, these are your uncertainties. And this is our last lesson in Unit 3. We're not going to do any more Unit 3 lessons until after your January exams. But I had to cover this anyway, just because there's so much past paper questions that involves your understanding of uncertainties. Let me give you examples. So I was doing with my students, I know time's over, but let me just go over 2 more minutes. I was doing this past paper with my students. Where is it? June 2019. And there was a 6-mark question. And it said, explain why the sample of wire used in the experiment should be long and thin. Generally in GCSE, when it says explain why you should use a longer wire, or explain why you should use a larger sample, or explain why you should change this, you talk about accuracy. In A-level, you no longer talk about accuracy. You talk about percentage uncertainties instead, because percentage uncertainties give you a lot more information than accuracy. right? Because it tells you the percentage away from the true value. So you don't talk about uncertainties and accuracy anymore. You only talk about percentage uncertainty. So for this 6-mark question in Unit 1, you had to realize that percentage uncertainty is equal to the uncertainty over the measurement. The uncertainty doesn't change because you're going to use the same equipment to measure the wire, which is a micrometer, and the length using a ruler. So because you're using the same equipment, the uncertainty doesn't change. But what does change is the measurement. If you measure a longer wire, you're going to have a larger measurement. So you're dividing by a larger value. So in this question, you're going to say a longer wire is going to lead to a smaller percentage uncertainty. And also a thinner wire is going to lead to a longer percentage uncertainty. And that's, I'm not going to talk about that because we haven't covered Young's modulus. But does that make sense how you still need to kind of know your uncertainties for Unit 1? You can't just completely skip it. Because a lot of the questions where it says explain why this should be changed, explain why he should use I don't know, a more dense fluid, or explain why he should whatever, you just have to basically say and talk about percentage uncertainties. And for percentage uncertainties, the larger the measurement, the smaller your uncertainty, i.e. the more accurate your answer, because you're dividing by a larger value. Does that make sense?
Yes, sir.
Good. So I will see you all on Tuesday. I'm going to upload the following homework. This homework here, this is on Stokes' law and viscosity, and it's going to be due Tuesday. So have a go. It's quite difficult. There is definitely a lot of difficult questions, but that's fine. It's not about getting the question right. It's really not. You're not at that stage. It's all about looking at the question, struggling, making mistakes, learning, understanding why you didn't get the question right and what can you learn from these questions. So yeah, this will be your homework. Any other questions?
Sir, can you send me the video from last lesson?
Oh yes, I recorded it. I tried to upload it on YouTube, then I had the error, but I'll try to upload it again.
Okay, thank you.
No problem. Goodbye, everyone.
Bye, sir.
Bye, sir.
Sir.